Question 7. Pretty standard looking shapes question. Probably going to be followed up by something about coordinate bonding if I had to guess. I have seen the paper before, but I haven't looked at it for a while. But it just, that's what it's sort of telegraphing. It suggests that there's going to be something about that. But first we need to answer the shapes part. So we've got ammonia and aluminium chloride. We've got to include any lone pairs of electrons that influence the shape, and we've got to include bond angles. So this is probably one of those scenarios where you need to get everything correct for 3 marks, and if you kind of slip up on one thing, it's 2, and so on. Okay? So, let's start with ammonia, in case we're wondering how to work this out. Hold on. Alright, here's our formula. Okay, that's pretty crucial because we're going to want to identify the central atom. That's the first step. It's going to be nitrogen because it's always the thing that you've got one of, or pretty much always the thing you've got one of. Okay? So the nitrogen is going to be the central atom. Nitrogen is a group 5 element, so it has 5 electrons in its outer shell. There are 3 things bonded to nitrogen, and we're assuming, because of the sort of keeping it simple perspective, that all of the things that are joined to the nitrogen are going to be joined by single covalent bonds. So what that means is each hydrogen atom that's attached to the central nitrogen provides 1 electron each. Okay? If this bothers you, then you can do a dot and cross diagram. That's totally fine, and it's a good way of working it out. A GCSE overlapping circles dot and cross diagram. But once you're confident with the sort of shapes method, you shouldn't really need to do it every time, and sometimes it causes problems when there are more complicated examples. It would work for this though. I'm just not going to do it because I don't need to, right? And you shouldn't need to if you're sort of confident with shapes after you've practiced them for a while. So then, crucial pieces of info. We've got a sum total of 8 electrons around the central atom. Electrons are always paired, so that means we've got 4 electron pairs. We then have to basically distinguish between bonding pairs and lone pairs, right? And the easiest way to do that, again, is to consult the formula. There are 3 things bonded to the nitrogen, and I said each of those hydrogen atoms is bonded via a single covalent bond, and a covalent bond is a bonding pair of electrons. So just to recap, 3 things bonded, each bonded via a single covalent bond. So there's 3 single covalent bonds, that's 3 bonding pairs. So by subtraction, we have 1 lone pair. Okay? This is what you arrive at, but you need the knowledge, which is that your basic shape, if you have 4 electron pairs, is going to be tetrahedral or some variation on it. It's not actually tetrahedral. It has a different name because it's not got 4 bonding pairs, it's got 3 bonding pairs and 1 lone pair, so it's a distorted tetrahedral shape that has a very specific name. Okay? So, we've got a central nitrogen, 3 hydrogen atoms attached, and a lone pair. That's still just 4 pairs of electrons, but one of them is a lone pair, hence the kind of balloon shape and the 2 dots. It's conventional to stick that on the top, right? And just to explain why, the reason you stick it on the top is that then you can kind of trace a line around the bonding pairs, okay? And that gives you an indication of the name of the shape, right? And the actual name of the shape is not tetrahedral, although you can often get away with that because it's very closely related. Instead, it's trigonal pyramidal because it is the shape of a triangular based pyramid. I probably should have said this at the start of the question, right? But if you don't know your shapes, there's literally no point in you watching this, right? If you haven't spent the time to learn, at the very least, the 5 basic shapes and the method for deducing what shape your molecule is, you're not going to get much from this, okay? So, if we give aluminium the same treatment, aluminium is the central atom. There are 3 things bonded to it via single covalent bonds. So that gives us a sum total of 6 electrons. That's 3 electron pairs. there are 3 things bonded, so there must be 3 bonding pairs. That means that there must be 0 lone pairs. So I went through that one fairly quickly, but it's using exactly the same series of sort of statements that we did for the ammonia. Okay, so this combination, again, if you haven't learnt your shapes, it's not going to mean very much to you, so you have to learn them. But anything that's got 3 pairs of electrons, whether they're bonding pairs or lone pairs, is going to be based on the trigonal planar shape. And in this case, it's pure trigonal planar. That's all it is, because all 3 of the electron pairs are bonding pairs. So we draw that completely flat. Okay, and it just looks like that. We don't need any 3-dimensional wedged or dashed bonds. Let's also point out that we need to mark on bond angles. 120 degrees for that. 107 degrees for ammonia. Okay? If you're wondering where those things come from, I'll just point out briefly, this is just something you learn, 120 degrees for trigonal planar. This one, you can just learn it, or you can learn the process, which is that if you did have a pure tetrahedral molecule, your bond angle would start at 109.5 degrees, and every time you introduce a lone pair into the structure, that reduces the bond angle by 2.5, roughly 2.5 degrees. Sometimes it's 2, sometimes it's 2.5. Okay? In this case, it was saying it's 2.5. So if you take 2.5 off 109.5, you get 107. And the explanation for that is to do with valence shell electron pair repulsion theory. Again, something you just have to learn, right? So, that's our 3 marks. Oh look, name the type of bond formed between nitrogen and aluminium in the compound H3NAlCl3 and explain how this bond is formed. So, I already mentioned this, right? Just to sort of justify this, if I just turn my ammonia molecule, I'm still going to keep the same 3-dimensional orientation just to be consistent. Okay, I've got a lone pair of electrons which is not currently attached to anything. If I redraw my aluminium chloride, something that often bothers students when we first start to learn about shapes is the fact that in a molecule like aluminium chloride, you only end up with 6 electrons around the central atom, not 8, like you've been kind of hammered to learn at GCSE. But that's right, there is still space for 2. So there's a kind of match made in heaven here. You've got ammonia with a nitrogen with a lone pair of electrons, and then you've got a space, essentially, right? Not necessarily that space, but some space around the aluminium atom for another 2 electrons. So that's what leads to the formation of this special type of covalent bond, which we call coordinate, sometimes called dative covalent, but I call it coordinate. Okay, explanation, we've already partly done that. Both electrons in the bonding pair come from, or are donated from, the nitrogen atom. Okay. Then we've got a question about how the bond angle changes on formation of this new compound, right? To do this, it's probably easiest if we kind of draw the whole thing. So I already sort of started with that. But if we think about something that's not geometrically accurate to begin with, just to show this, you could represent this molecule by using this kind of diagram. And the arrow here, that's to show the coordinate bond that we've just explained in words. That's, tells us that the lone pair in the nitrogen is being used to form this covalent bond with the aluminium. Okay? The simple way of looking at this is it's asking us about the bond angle in AlCl3. So this started at 120 degrees, that's what it was. And then it says changes if at all. Well, it does change. Okay, so that's the first thing to sort of figure out. Okay, and we need to provide an explanation as to how and why. So go back to the working. from the very first part of the question. We said that there were 3 bonding pairs around the aluminium and no lone pairs, right? And that basically means that they occupy 1/3 each of a circle, if that makes sense, 120 degrees. In this configuration, there's no longer 3 bonding pairs around the aluminium because we had 1 before, 2, 3, but now we've got a 4th one. It's a special bonding pair because it originally came from the nitrogen, but it doesn't matter, it's still just a bonding pair of electrons. So that means we've now got 4 BP. If we go back to the working again, if you remember, here we pointed out that anything that's got 4 electron pairs, bonding or otherwise, must start out as a tetrahedral shape, and actually if it has 4 bonding pairs, it is pure tetrahedral. And that's just with respect to the aluminium, right? It's just centering on this atom. Okay, actually the nitrogen will be tetrahedral as well now, but it doesn't really matter, that's what we're being asked about. So, just to clarify again, there's your aluminium. Now, your chlorines are not at 120 degrees, in fact none of the bonding pairs are, okay? And I'm going to keep that as an arrow, and I'm going to condense the rest of the molecule into NH3, just to keep it nice and neat and tidy. And you should be able to see that that's a tetrahedral shape. Earlier I mentioned what the bond angle was in a tetrahedral molecule. 109.5 degrees. Again, you've got to have learned that. So, I'm not going to write this out in words, but it decreases from 120 degrees to 109.5 degrees. There are now 4 bonding pairs. Around the aluminium. So there's more repulsion. In other words, the bonding pairs that were there initially and this new one that's just been added, they all get pushed slightly closer together because there's basically less space per bonding pair, right? Because 3 bonding pairs, they had all this space to occupy. You add in another one, the rest of them have to go closer together. And they'll all be equal, despite the fact that one of them is a coordinate bond. They'll all be pretty much equal. Sometimes the atom that's on the end of the bond does have a bit of an influence, so it might not be exactly 109.5 actually, but it'll be pretty damn close. Okay? Good.